In this video, I'm going to discuss about Hooke's law. So Hooke's law is associated with the spring constant, distance stretched, as well as the force required. So let me draw a spring first. A vertical spring. Have you ever wondered how much force is required to stretch another maybe 1 meter? Well, Hooke's law can solve this question. How much force is required to stretch it 1 meter? So Hooke invented this formula called Fp, which is the force required to pull it, equals K, which is the spring constant, and X, which is in meters. If you know the SI international units, it's always in meters. FB is in newtons, and K is always in newtons per meter. So I'm going to delete all this. Hopefully you copied that down. So this is the formula you want to remember. Fp equals Kx. So like right here, we have our example. Let's just say the spring constant is about 250 newtons per meter. How much force does it require to pull 1 meter? Well, you can use this formula right here. Fp equals K, which we know is 250 newtons per meter. Just gonna write 250 tons per meter. Then times by X, which is the distance. So the distance traveled is what we want to stretch is 1 meter. You're gonna times it together and you will get your answer you need. So Fb equals 250 newtons to stretch it 1 meter. Now, if you want to find, you can also find other forces you need to require to stretch 1 meter. So, if I say, we know that to stretch 1 meter, you need 250 newtons. But how about half a meter? Well, you can just divide it by, so half a meter is, so a meter is 100 centimeters. And half a meter is 50 centimeters. So you can try it out yourself. How much force is required to stretch the string half a meter? So you can take your time. You don't need to do this, but it can help you. Okay. Now, there are other stuff I also want to talk to you about. This is not only about finding the force required, but it is also about finding the spring constant. You can also find the distance traveled. Distance stretched, I mean. So let's start with the K, which is the spring constant. I'm going to draw another diagram. So let's just say that we have a spring that yeah, just this, and we will stretch it 2 meters. And we're finding the spring constant, so we have to know the force required. So let's just say we require 500 newtons per meter. So what is the spring constant? Not newtons per meter. It requires 500 newtons to stretch 2 meters. So we can plug everything in, what we know. So FB is 500. And it equals to 2 meters, which, no, never mind. K, which we're finding, and 2 meters, like this. And then you would divide 500 with 2 meters, and you would get, so K would equal to 250 newtons per meter. Okay, next we're going to do the K. Not the K, I mean, we already did the K, the spring constant, but we're going to do the distance now. So if I'm going to do this, delete that, delete this. I'm going to keep the diagram the same so we don't waste time. This is, let's say we're stretching at 5 meters. And the spring constant is 500 newtons per meter. What is the distance? Oopsies. Sorry, it's not, we don't need this, we're finding x, so. Okay, and we require it, and we want to find the distance here. And to get from here to here, we stretched about, let's say, 1,000 newtons. So we just plug in what we know. FB is 1,000 newtons. That would equal to K, 500, and finding X. To do that, we're going to divide 1,000, 500. Sadly, I don't. Okay, never mind. So you would know that X would equal to 2 meters. Because 1,000 divided by 500. It has to be a meter because it says 500 newtons per meter. If it says newtons per centimeter, it has to be in centimeters. Okay, now that we know what to do, I'm going to explain the forces acting on the spring when you're stretching it. So let me draw a completely new diagram. The spring's here, and there's a spring. Oh no, that's not good. That's better. So the forces acting on this are nothing. But if you do count gravity, yes, that's a force acting on this object. But let's just pretend weight does not matter. And this guy, has no force acting upon it. Now we'll call this X for now. And what happens if you stretch it? You're stretching the same spring right here. What forces will be acted upon this? Well, you can say that since you're pulling it, the force right here, this is called FB. FP, I mean. That's one force. And FB is equal to the positive side. Going to the right, so that's positive. And there's another one called FS, which is returning to its original place. and that is in the negative direction. Okay, so, and I just want to also say that FP is also equal to FS. They have the same magnitude. Because since you're pulling this much, FS also wants to go this way as well. So they have the same magnitude. And I think that's going to wrap it up for the introduction part 1, whatever you like. And I'm going to prepare some questions for you. It's either 3 or 4. I haven't wrote them yet, but I'm going to write them soon. So I'm going to meet you on the question side. Okay, so this is the next question. How much work is required to stretch a spring by 75 centimeters? And the K is 250 newtons per meter. Now, if you've learned work, you would remember it equals W equals FD, force times the distance. But it's a bit complicated to turn W into the right formula, so I'm just gonna skip all that messy stuff. It's very complicated, trust me. So once you're done all that complicated stuff, you will come to the end of W equals 1/2 of Fx. Now, of course, I'm gonna show you part of it, so you don't like miss out on all the stuff. So, we know that F equals Kx. Actually, yeah, keep FP, I think that's a better. FP was Kx. And then you rewrite it into W equals 1/2 of, in parentheses, K, times the change of X, times the change of X again. Now, when I mean the change of X, you can view this as here. This is the change of X, delta X. Because this is X and this is X, and you're finding what the change of X is. Hopefully that makes sense. I know it might not make sense right away, but you get the point later. So I'm gonna draw, actually not draw. So this is not the real formula, not yet. I'm just doing some of the stuff. And then you would come to this 1/2 of K delta X squared. Because if you think of it, delta X times delta X is equal to delta X squared. So let me go down a bit. So W would equal to 1/2. We know that K right here is 250 newtons per meter. So we're going to times 250 newtons per meter. Newtons per meter. And as well as the change in X. So the change in X is, go up here, 0. It's 75 centimeters. We gotta convert it into meters, so 0.75 meters in the squared. So you're gonna do this one first. Actually, I'm just gonna write down the answer. So the work required, once you've done all the math, I don't have my calculator on me. So I know the answer. So after you've done all the math, calculate it on your calculator or on a piece of paper. Hopefully you got the answer 70.3 joules. So work is in joules if you didn't know. And I know I said that I would have 3 or 4 questions prepared, but I only have 2 today. Hopefully that doesn't bother you or make you mad, but you can always make questions yourself. So you get a little bit curious and start to like the law. If you do hate it, I don't know what to do, honestly. Okay, that's gonna wrap it up for today's video. If you guys enjoyed, and so gotta say, bye.